So the nuclear chemistry worksheet, very small amount of content, of course, associated with nuclear chemistry on the A-level spec. So there's a lot of repetition in this, but it's always good to practice. So anyway, so question 1, we've got a two-stage process by which radioactive uranium, all isotopes of uranium are radioactive. So that was a redundant use of the word radioactive. But anyway, first thing is it loses an alpha particle, right, mass of 4, charge of 2. The way that you balance out the equations for nuclear processes, you don't balance out individual atom types, because the whole point is that they change. What you do is you balance out the mass and the charge. So the mass of our new one, well, we started with 238, we've lost 4, so it must be 234, and the charge of the new one, we started with 92, we've lost 2, so it must be 90. The element that has a nuclear charge of 90 is thorium, so this is thorium 234, and now this loses a beta particle, so the mass of the new one is going to still be 234 because a beta particle doesn't affect the mass, but when you lose a beta particle, the atomic number, the charge, has to go up by 1 to account for that. So started with 90, we end up with -1 plus 91. 91 is protactinium, so 234 Pa. 226 is radioactive, again redundant. All radium isotopes are radioactive, decays by alpha, has a half-life of 1600. So mass number of the symbol of the species formed by the loss of 1 alpha particle from, well, an alpha particle, as we set up here, has a mass of 4. Thus, you're going to lose 4, thus you're left with 222. Charge-wise, you're going to, should be and not of. Charge-wise, you start with 88, you lose 2, so you're going to end up with 86. So thus our new species, 86, is radon, and so 222 radon. What's the half-life? Time taken to use up half of the amount with which you started. And a sample of initial mass 1 grams, K's for 3200 years. Calculate number of moles of radium left after this period. So we know that the half-life is 1600 years, 3200 is twice that, so that's 2 half-lives. So we start with a gram, so therefore after 1 half-life we'd have half a gram, after a second half-life we'd have half of a half, or a quarter of a gram, so 0.25 grams left. We want number of moles, so we have to divide that by the molar mass, 226, don't even have to look that up, and we get 0.00111 grams. Half-life of radioactive is 15 hours, decays by beta emission to give a stable isotope of magnesium. Now this is a fun one, because what we're doing here is we're starting off with the isotope, we don't know what it is, 24Z, and it's giving us some magnesium 12 and an a beta particle. So we have to look at the charge here. 12 and -1 means that X has to be 11. 11 is sodium. And so the mass of this would of course be 24, because there's no mass change when you do a beta elimination, but it didn't ask for that, it just asked for the atomic number sodium and symbol 11, or other way around, atomic number 11, symbol sodium. Period of 48 hours, only 0.15 grams of this remains. Calculate the starting mass. Well, the half-life is 15 hours, 45 hours therefore is 3 half-lives. Well, after 3 half-lives, you've got 0.15 left. So after 2 half-lives, you have twice as much as that, 0.3. After 1 half-life, you'd have 0.6. So after 0 half-lives, you'd have 1.2. As you go from 1 half-life to another, you divide by 2. So as we count backwards, we multiply by 2. Half-life of this is 2 minutes. Okay, so 15 oxygen kicks out a positron. So this 15 oxygen kicks out a positron. Let's look at the mass of the new one. It has to be 15 because a positron, like beta emission, doesn't affect the mass. Charge of the new one, well, you've got 8 here. You've already used up 1 of those, so there's 7 left. So that means that it is 15 nitrogen. Nitrogen is the atom that has atomic charge of 7, atomic number of 7. Quantity decays by positive. What fraction is left after 10 minutes? Well, 10 minutes is 5 half-lives. So 1 half-life, you've got half left, 2, you've got a quarter, 3, you've got an 8, 4, you've got a 16th, and 5, you've got a 32nd, because we're just halving each time. 33 known isotopes Krypton, jolly good for Krypton. 1 decays by electron capture. So we take 81 Krypton, which has got an atomic number of 36. We have it now react with an electron, okay? And so our new nucleus is going to have a mass of 81 because we've got a total mass of 81. And the atomic charge, the nuclear charge, excuse me, is going to be 36 minus 1, so that's 35. 35 is bromine, so that's 81 bromine. Again, we've got now to look at the half-life, okay? It takes 6.87 times 5 years for 2 grams to decay to 0.25, calculate the half-life. Well, at 0 half-life, we've got 2 grams, so after 1 half-life, we'll have 1. After 2 half-lives, 0.5. And after 3 half-lives, we have 0.25. So in other words, it takes 3 half-lives to go from 2 grams to 0.25 grams. Or in other words, 6.87 times 10 to the 5 years is 3 half-lives. So 1 half-life, 6.87 times 10 to the 5 divided by 3, 2.9. 29 times 10 to the 5 years. Okay, so a question that I don't really like the way the A-level board does it, but so be it, right? Which of these isotopes is the most suitable to lose as a tracer in medicine? We got 2 things to think about here. First is you want it to be detectable, right, but go away. So you don't want something that's going to have a really, really long half-life, okay? So that knocks out the 28 years and the 1.9 years half-lives. You want it to do its thing and then be gone. Now, the second thing is the one I kind of have an issue with the way it's phrased. You want your tracer, right, to leave. You don't want it staying in the body banging around like crazy, okay? Now, of course, gamma radiation gets out of there and leaves. Alpha particles bang around in there and do more cell damage and so on. The other thing is, of course, that gamma particles can leave because they're very penetrating. Alpha particles can't penetrate squat, and so therefore it's much easier to detect gamma rays outside of the body because the alpha particles can't actually get through the skin to be detected. So with all that, you get rid of the alpha and you keep the gamma. Thus 99 technetium is the one on this list. 99 technetium, arguably the most important radioisotope in terms of its use in medicine as a tracer. So, question 29, magnesium 28 decays by beta. So, 28 magnesium kicks out a beta particle. Mass of the new particle 28, charge of the new particle 13, so therefore 28 aluminium. And now, part B, 84 hours to decay to a 16th. Or 1 half-life gives you a half, 2 is a quarter, 3 is an eighth. After 4 half-lives, you have a 16th back. So 84 hours is 4 half-lives. Thus, 1 half-life is 84 over 4, or 21 hours. Now we're off the A level and into my type questions. Which nuclear equation properly balanced? Well, you just have to look at the charge and the mass on both sides. When we look at A, we have 4 plus 9, 13 mass. 2 plus 4 is 6 charge. Over here on the right hand side we have 13, of course, for the mass. That's still fine, but we have a charge of 7. This shouldn't actually be a proton, it should be a neutron. If you have a neutron there, then your charge becomes 6, but silly person put in proton, so this is not the right equation. B, charge of 18, sorry, mass of 18, charge of 9 on the left, 18 and 9 on the right. Just make sure you can add them all up. 4 plus 14 is the same as 17 plus 1. 2 plus 7 is the same as 8 plus 1. For C, mass of 28, charge of 14 on the left, 28, 15 on the right. Again, if this were a neutron, everything would be wonderful and balanced, but it's not, so this is not right. And finally, 14, 6 on the left, 14, 8 on the right. Your charges are out of whack completely. When nitrogen 14 accepts an electron, captures an electron, it will make 14 indeed for the mass, but the nucleus will be carbon 6. Or nucleus will be carbon because it has a charge of 6. Spontaneous, you have an alpha particle, new nucleus, so same thing, that's 94 uranium or 234 uranium, kicks out an alpha particle, giving you 238 and 90, so thorium, so 238 thorium. So strings of questions balancing the equations. We've got an equation which we take a lithium isotope, bombard it with protons, and we make two somethings. So mass on the left is 8, charge on the left is 4. There on the right, the two of them have to be 8 and 4, so one of them will have to be 4 and 2. In other words, a helium nucleus or an alpha particle. Question 11, we have two successive losses of beta particles. Beta particles don't change the mass, but they increase the atomic number by 1 each time. Remember, beta particle elimination effectively turns a neutron into a proton. So 239 and 92 at the start. Y would be 239 and 93. Z would therefore be 239, 94. 94 is plutonium, Pu. 239, plutonium. Nuclear reaction here, what is X? Well, again, mass on the left is 14, charge on the left is 7. So the mass on the right has to be 14, the charge has to be 7. Right now we've got 7, that's fine, so X doesn't have any charge, but we need another mass. So X is mass of 1, charge of nothing, otherwise known as a neutron. 238 or 232 thorium itself particle. So let's see, standard old thingies. The mass of the new one's 228 because we've lost 4. The charge on the new one 90 minus 2, so is 88. That's radium. So 228 radium. Missing product particle, where we take plutonium, bombard it with an alpha particle. So let's put in the appropriate charges here. So 92 plutonium, helium 2, and of course we had a neutron over there with 0. Mass on the left is 243, charge on the left is 96. So the total over here must be 243 for the mass and 96 for the charge. Well, we already have 1 in the mass, so the new one's going to be 242. The charge, however, is unchanged when you lose a neutron. So our new nucleus, 242 curium. Alpha emission by lead 204 results in the product isotope, so same old question. Mass of the new one 200, charge of the new one 80. 80 is of course mercury, so 200 mercury. And from the other direction, what's a missing reactant? Well, again, let's put in the appropriate charges. Nitrogen is 7, carbon is 6, and hydrogen is 1. Mass 14 and 7 currently on the left, 15 and 7 on the right, so we need an extra mass here, so thus this is a neutron. Now we go into determining which things are radioactive or not. So various things to look at. The first is size, and then the appropriate ratio for the smaller nuclei, smaller than 83. Looking at the neutron to proton ratio, and the way you can tell the ideal neutron proton ratio for a particular atom type is to just look at the mass on the periodic table. So the mass on the periodic table for potassium is 39, so 39 potassium is almost certainly stable. Mass for aluminium 27, so 27 aluminium, almost certainly stable. Mass for iodine is 127, so 127 iodine almost certainly stable. And then you get to americium, which has got a nucleus that is bigger than 83 protons in there, so by definition it's going to be radioactive. Soon as you've passed bismuth, if you remember that part of the discussion, soon as you're past bismuth, every single isotope of every atom is radioactive. Nucleus most likely be stable when it has even and even numbers of neutrons and protons. Even is good, odd is bad. As the relative numbers in the movies, the one that stands out is that there are only 4 stable nuclei that have odd protons and odd neutrons. Expected decay of 39 Cl. Well, chlorine's atomic mass on the periodic table is 35.5. So the mass of this isotope is bigger than the ideal mass. Now, it's not so much bigger that you might automatically say, oh, it's radioactive then, but you're told it's radioactive. Okay, so it's radioactive, the mass is too big, and so therefore it will decay via beta emission, because the mass too big means you've got too many neutrons, not enough protons. You want to turn a proton from a neutron into a proton. So 39 Cl is going to kick out a beta particle, leaving behind. Mass of nu will be 39, charge of nu will be 18, okay, because beta, of course, raises the atomic number, so it's argon 18. Beta emission, we just talked about this. It decreases the neutron to proton ratio. It turns a neutron into a proton. Doesn't have anything to do with the mass number, or doesn't decrease the atomic number. It increases the atomic number. Right, if a low lies above the band of stability, if above the band of stability, that means it's got too many neutrons. So again, for the third question in a row, that means it will undergo beta emission. Last few questions on half-lives, fairly straightforward. So we start with 20 times 10 to the 10 atoms. After 16 days, we've got 5 times 10 to the 10, well, at 0 half-lives, 20 times 10 to the 10, 1 half-life, 10 times 10 to the 10, and 2 half-lives, 5 times 10 to the 10. So after 2 half-lives, this is what we've got. So 16 days is 2 half-lives, 1 half-life is 8 days. Half-life bismuth, 19.7, starting with 10 to minus 3 grams. How many grams remain after 59.1 minutes? Well, 59.1 divided by 19.7 is 3 half-lives. It's a good thing it's a whole number of half-lives, because you don't know what to do when you have a fractional number of half-lives. But anyway, 1 half-life. After 0, you got 10 to the minus 3, 1, 5 times 10 to the minus 4, half of that. Half it again, 2.5 times 10 to the minus 4, 3, half it again, 1.25 times 10 to the minus 4. That is what you got left after 3 half-lives. So half-life should be an isotope of francium, 19 minutes. How many minutes for a substance to decay to 1/8 of its original activity? Well, after 1 half-life, we have a half, 2, we have a quarter, 3 half-lives, we have an 1/8. So we need 3 half-lives. 3 times 19 is 57 minutes. And finally, iron 59, radioactive isotope, half-life 46 days. Initial count, so here we're talking about counting it rather than grams or moles or whatever. 560 counts per minute. How long to 140 counts per minute? Same idea. After 0 half-lives, 560. 1 half-life, half as much. 2 half-lives, another half as much. So it takes 2 half-lives to get down to 140. 1 half-life is 46. 2 half-lives are 92 days. So a 17-minute run through, relatively straightforward. All you need is to have a handle on about 3 different concepts. Hopefully it made sense. See you in the next one.